question for you. So, imagine this. Question for you. So, imagine this.
Dark matter. Dark matter. Dark matter.
Dark matter.
Dark matter. Dark matter. Dark matter.
There is a not so bad reason why we are looking for it and why we all think it exists, why something exists that is dark in at least one way, that we can't really detect it. We more detect its effects. Basically, from the smallest scales here in our neighborhood out to the cosmos, we see evidence of something without a guilty party, so to speak, without an actor doing it. And so this is our dark matter in terms of the gravitational effects. And then there is the dark energy, which seems to be expanding the universe, at least from our scientific perspective.
How to make a galaxy? The ingredients are dark matter, and then stars, and then gas.
Dark matter makes up about 85% of the mass in the universe. So our best idea for what dark matter might be is that it's some kind of subatomic particle. We don't know what kind, but there are several good ideas which come out of particle physics that provide good candidates for dark matter. And we're looking to see if we can actually detect one of those in the lab.
The leading detectors for trying to find this, the most sensitive, are liquid noble gas, like xenon or argon in liquid form.
We have our milk carton here.
It's not there. It's just not. This dark matter model is probably not completely correct. Thinking all these together, it poses a real problem to our understanding of cosmology.
The direct searches are pushing to masses higher than the LHC can reach, and also to cross-sections, interaction strengths that are very weak, much weaker than the standard weak interactions. And that's the direction we push down in interaction strength, and either up or more recently also down in mass. So down to below the mass of a proton or up to the mass of 1,000 protons.
We have had to sort of invoke some tooth fairies to keep things sensible. One of those is dark matter. Supersymmetry is my favorite example. It was a beautiful idea, very compelling, was basically accepted widely in the 80s. All the predictions that supersymmetry made have failed badly. And the most popular form of dark matter, the WIMP, is a supersymmetric particle. So you only have WIMPs if you have supersymmetry. And so now we've gotten to this weird point where most people seem to have forgotten that you need supersymmetry to even have WIMPs. Now we have WIMPs because we know we need to have this dark matter, but the supersymmetry that is required to make those things exist doesn't work. And it's failed in lots of ways.
Everything goes back to Newton. Newton didn't just discover the inverse square law. He discovered two more things. One was that knowing the luminous distribution, namely knowing the sun, you could predict the velocities of all the planets. No dark matter. It's absolutely clean and straightforward. That, in my opinion, is the gold standard for what you need to do in any theory of gravity. You have a law of force, you know the visible material that you can see, and then you have to predict the velocities, predict exactly what's going on. That's step A. Step B, he proves a theorem. It's a very interesting theorem. And it says this: if you have a spherical distribution of matter and you want to know the force at any point, then the only contributions are coming from material within the region where the object is located. Nothing is coming from the outside. The outside absolutely decouples, and therefore, if you wanted to solve for the solar system the way he did, you didn't need to consider any other sources. Okay? Now, the mathematical reason why this happens, the inverse square law force falls like 1 over the square of the distance. But the solid angle grows like the square of the distance, and therefore they cancel. Exactly the same thing happens for Coulomb's law in electromagnetism. So with Newton's law, we have two remarkable things. One is knowing the luminous distribution, you get the velocities, and two, you don't need to include anything outside the system of interest. Now, dark matter keeps the second rule, but not the first. In other words, dark matter says we only need to know what's going on within the system itself, but we don't have to restrict to luminous matter alone. In other words, you give up the Newtonian gold standard right away. And that, to me, is not good physics. Just simply point blank, that is not the right way to approach the problem. Now, a way to think about this, which is very simple, but of course not the complete story, is if you have the inverse square law, then it's true on all distances, including r equals 0, namely at the origin, which means that a particle acts back on itself. We worked for 6 months. The equations are quite complicated, and we managed to solve them, and we found the exact solution. Yes, we got the inverse square law. But we then got something that we absolutely hadn't anticipated, namely we got a second force, and that second force was not vanishing at large distances. The inverse square law gets smaller and smaller. It goes like 1 over the square of the distance. This second force was constant. It did not fall off at large distances. We looked at that. It took us 6 months to find the equations. It took us an afternoon to solve them. And when we got the solution and we saw this extra term, we realized immediately that we could replace dark matter. And that wasn't what we were looking for. And it took me many years to understand this. It took me a lot further steps. I gradually realized that because I had this force which did not vanish at large distances, Newton's theorem that I can ignore the outside no longer holds. And therefore, the outside must be playing a role. The notion that we can neglect the outside only comes because of a very specific law of force, namely Newton's inverse square law. Any other law of force, you can't neglect the outside. So, if you now go back to the early studies of galaxies, where people measured velocities and found that the velocities were more than they could manage, and so they went on to say, okay, there must be some missing mass. What I say is, it's not missing. It's the rest of the universe. It's been there all along, and it's hiding in plain sight. And you just didn't recognize it as such. And therefore you should not conclude that dark matter is doing the job.
But this problem with the too early appearance of galaxies actually goes back a couple of years, and there were already hints that there were major issues with the standard model. And basically, to put it in a nutshell, what it is that in the standard model of cosmology, there's a very firm prediction of what the timeline has been since the Big Bang. And the problem here is that these massive galaxies and the massive dark matter halos from which they formed appeared way too early for standard astrophysics to be able to explain how they came to be. So just to put a number on this, because it's a lot easier, I think, to understand in terms of actual numbers, the redshift at which they see these massive galaxies and halos, which is around 10 in the case of Charles Steinhardt's work, that corresponds to an age of the universe of around, let's say, 600 million years after the Big Bang. And remember that the age today is about 13.7 billion years. So we're talking about something very, very early in the history of the universe, 600 million years or so. The reason that's a major problem is because, as we understand it today, stars could not have started to form until about 3, maybe 400 million years after the Big Bang, because it would have taken that much time for the gas to cool and condense and clump up and form stars. So basically what the data are telling us is that if the standard model of cosmology is correct with its timeline, then these 10 to the 9, 10 to the 10 solar mass galaxies, billions of solar masses within each galaxy, formed in only 150 to 200 million years, which is absolutely physically impossible as far as we know today, based on the astrophysics of star formation and aggregation and the formation of galaxies and so forth. But to be fair, there were other indicators even before Steinhardt's work that showed that there was a problem with the timeline. Perhaps most famously with the appearance of these supermassive quasars, these supermassive black holes, which started appearing at a redshift of 6, and then today the record is about 7.4. That redshift corresponds to about 800 million years. And so the indication from the appearance of these supermassive black holes so early in the history of the universe is that these billion solar mass objects formed in only 500 million years, which again is not easy to understand in terms of the astrophysics that we know today. The conundrum is that we see these objects, either black holes or these massive galaxies, way too early, and in order for us to be able to explain how they formed in such a short time, we have to exceed what we think can actually happen in terms of the astrophysics of accretion and growth and so forth. So the conclusion from this is either that the astrophysics we have today is wrong, or what we're suggesting is that perhaps the cosmology is not completely right. Ironically, Charles Steinhardt's father, Paul Steinhardt, was one of the inventors of inflation, and Paul Steinhardt is now a total convert the other way. He thinks that inflation is wrong. Even though he was one of the inventors of that, he's actually an inflationary apostate, if I could put it that way. He argues against it.
When things go wrong, you have to bear in mind that maybe we got something wrong along the way, or missed something that is important.
Kirchhoff's claim, if you have a cavity and you're in thermal equilibrium with that cavity and the cavity is opaque, the radiation will always be the same inside that cavity, depending only on the temperature and the frequency and independent of the nature of the walls. The ratio between emissive power and absorption power is the same for all bodies at the same frequency, at the same temperature. And then Kirchhoff immediately sets the absorption to 1. So this is an idealized state. And I understand, as anybody who's taken a modern physics course, that this is, Kirchhoff imagines something that's a perfect emitter and he sets absorption to 1. But if I set it to 0 in the perfect reflector, as we hope to have when we do MRI, then that function blows up. So perfect reflectors definitely cannot support Kirchhoff's claim. And remember, he said it was independent of the nature of the walls. But this is the key thing, and this is what has been missed by physics, is that real black bodies can do work, and perfect reflectors cannot. So we depend in MRI on having a perfect reflector. We don't want it to do work. We don't want our coil to do work on our radiation. We just want it to transmit it, right? And that's the same thing for lasers. In lasers, you have mirrors, and these mirrors are building up waves between the mirrors, and they have quality factors of 10 to the 11th. Now, to tell you what that is, a quality factor of 10 to the 11th, that means it'll hold for every 10 to the 11th wave it's standing, it'll lose 1. Well, that's perfectly reflecting, right? 10 to the 11th, no black body has ever approached these kinds of numbers. So perfect reflectors exist, and they're telling us that Kirchhoff cannot be right. So real black bodies can do work, perfect reflectors cannot. And here's an example where I take this block and I put it on a hot plate. The bottom 4 are copper, then graphite. I think the next one is aluminum and then brass. And you can look in the paper for the assignments. But look at the graphite holes. They're all white. Now, they have different depth. The holes on the right, the 4 holes on the right, 3 are black and 1 is white. The one in graphite is white. Those holes are just the tip of the drill bit into the block. That's all that there is there. Okay? And then as you go down, I think the next hole might be a 1/4 inch, 1/2 inch, and 1 inch. Okay? So as you go down the hole, as you go to the left, the holes get deeper. But what are you seeing here? All this block is sitting at the same temperature. It's been sitting on a hot plate for hours. Okay? So it's all come to thermal equilibrium. It's at one temperature. Now that Kirchhoff had said that all the holes should look the same, but they're not looking the same, right? The little graphite hole on the right is already white, but the 3 from the perfect reflectors are not. Why? Because they're manifesting what radiation is in the room, not in the hot plate, right? It's what's in the room that's penetrating these things, and they're not able, they can't do work, so they can't produce the white radiation that the graphite hole did. Okay? So the graphite is white because it did work, and the other 3 could not do work, and that's why they remain black. And then as you go over to the left, you see that now it's a mixture of radiation coming in from the hot plate that's captured in the hole, and then radiation from the room. So that's why you now see these crescent shapes inside of this. There's 2 types of radiation in here. One corresponding to the temperature of the room, and the other one corresponding to the temperature of the hot plate. So again, this proves that Kirchhoff cannot be right. And the reason is that the perfect reflectors are unable to do work. They'll sustain whatever radiation is given to them. It has nothing to do with thermal equilibrium. So only graphite was able to do work, and perfectly reflecting cavities will display incident radiation. So if I can only convey this message to the world, this would be it. That because of Kirchhoff's law, Planck's equation remains unlinked to the physical world. And this is a central thing here. That Planck wrote an equation. So we had this light, and Planck gave us the equation for it, okay? But he never told us what caused the photons. What was the physical setting? What were the energy levels? What were the transition species? But in every other spectroscopic method, and I'm a spectroscopist by training, we can always identify these first 3. But because of Kirchhoff, and it's independent of the nature of the walls, Planck's equation was never linked to the physical world. Now, the reason that's important to you is it enables solar physicists to say that we can produce a black body spectrum from anything, or it enables the Big Bangers to tell us that they can get a black body radiation from the creation of the universe. They can't. Once you link these things, once you explain why do you get a thermal photon from graphite, whatever mechanism you use, everyone will be bound by it. So all of this theory will collapse. So this is actually a terrible blow to astronomy here.
The picture that we have of the CMB today is that it was the CMB was produced as a result of decoupling. When radiation decoupled from matter because the various charges combined to form neutral hydrogen and so forth. And the picture is that all of this happened about 380,000 years after the Big Bang, very, very early on, right? Much earlier than star formation and eventual galaxy formation and so forth. But the honest truth is that this is all theory. We don't actually have any hardcore evidence that that's really where the CMB happened, where it was produced, and that was the mechanism that produced it. We don't see recombination lines, for example. And it's true that the sensitivity of the instruments is not yet great enough for us to have conclusively detected the lines, but until we actually see recombination lines, this idea that the CMB was produced by recombination is just a theory. There's no experimental verification that it happened. And perhaps even more tellingly, if the picture of the CMB having been produced early on as a result of recombination is correct, then there shouldn't be any frequency dependence in the fluctuation spectrum. In other words, the spectrum was produced in a medium where the most important physical process, Thomson scattering, is independent of wavelength of the light. But yet, when we look at the data from Planck, say, we do see evidence that the spectrum of fluctuation changes with wavelength. So that again argues against the recombination picture. We don't have a compelling argument yet, but what I'm getting at is that this notion that the CMB was produced 380,000 years after the Big Bang due to recombination does not have yet any experimental confirmation. On the other hand, it's possible that the CMB may have been formed in part due to dust processes. And if you look back and ask when would the dust have been injected into the intergalactic medium, it would have been at the time when population 3 stars started forming, which actually corresponds to a redshift of about 15, not the redshift of 1081, which is what we currently think is where the CMB was formed.
This is the Penzias and Wilson antenna, the horn antenna at Crawford Hill Laboratory that the measurement was done on. And we won't read this whole thing, but basically it says we got a 3.5 Kelvin signal and we couldn't explain it. And nowhere in the Penzias and Wilson papers do we talk about diffraction of signal into the horn. So nowhere in the Penzias and Wilson papers of 1965 can one find any discussion of the diffraction of nearby signals into their horn. Now people wonder, well, how did an NMR guy get into this mess, right? And here's the answer. So Ed Purcell is the discoverer of the 21 centimeter hydrogen line in the galaxy. He discovered it 1 year before he won the Nobel Prize in 1952 for NMR. So we're both dealing with radio techniques. They're doing spectroscopy, so am I. It's basically our samples are different. And this is a picture of Ed Purcell's horn that he used to detect the 21 centimeter line. So these fields are actually much closer than people would imagine. So to tell an MRI person that he cannot look at astronomy is just a little too far reaching, considering that Ed Purcell was one of the first radio astronomers. Here's a radio telescope from the University of Illinois. Well, that's kind of exposed to everything, right? That could be coming in from the side. Here's the scoop antenna at Green Bank, which was used to monitor atmospheric changes. Well, that's pretty much the Penzias and Wilson antenna, pretty much the same kind of design. There's nothing sophisticated here. So COBE, the COBE satellite, is completely unshielded from microwave radiation from below, which can easily diffract into the COBE horn, the Pheris horn. Significant diffraction problems are very likely to exist for every other instrument on Earth except one. So now we come to Harouni's antenna. And people have attacked that, hey, this is just an old antenna here. Who cares about a result from an old broken down antenna? Well, when the result from Dr. Harouni was done, it was not a broken down antenna. It was new and he was testing it. And then he found that there was no signal from space. So how could that be? So this is showing inside the antenna on the right here. You see the detector. So this is actually 5 meters across, because this is not a parabolic antenna, it's a hemisphere. So it doesn't focus onto a point. So the signal comes into kind of a bell-shaped detector here, which is deep within the antenna. Okay, so that's very different than the parabolic antennas that you've seen. Okay, so what's important about that is his antenna self noise was only 2.6 Kelvin. So it has to have some self noise. So where's the signal from the Big Bang? You're missing. He should have had 6 Kelvin or so. He called it an edgeless radio telescope. So that's why it's unique. So any signal that's approaching from this side, it's edgeless. It's going to prevent diffracted signal from coming and hitting the detector. So note how the detector is protected from most diffracted signals. And again, if you look at a modern radio telescope, they're above ground. They do nothing to prevent diffraction, and their detector is wide open. It's imprudent to speak in terms of black bodies without noting, as Kirchhoff did, the constraint of the enclosure. So the astronomers, they need an enclosure, and what they tried to say is, well, we did have thermal equilibrium at recombination. Well, this is just an invention of mathematics. They don't know that. Kirchhoff's law is his requirement was very severe. You have to have an opaque enclosure. So thermal equilibrium with an opaque enclosure, not just thermal equilibrium. The enclosure must be opaque. Well, that never existed in the Big Bang. So you cannot set a temperature. A source which is not at 3 Kelvin can produce such a signal if it sustains, in addition to emission, another means of contending with internal heat, namely conduction and convection. Alternatively, a source which is not at 3 Kelvin can produce such a signal if it has structure wherein one bond is much weaker than another. And of course, I've argued that this signal is coming from the Earth. So I especially like this quote by George Smoot. So he's testing a radiometer at Berkeley, and this is what he writes. An invisible patch of water vapor drifted overhead. The scanner showed a rise in temperature. Good. This meant the instrument was working, because water vapor was a source of stray radiation.
We don't quite understand how much of the dust, how much of the light from stars is being absorbed by dust, and where exactly that happens. And so we have different measurements of how much millimeter light there is, so far infrared light there is from the dust, and how much light we think is missing, and then how much light actually is missing. And that's where the problem, like we were trying to tally up the light to make sure that we know how much is missing and how much is being re-emitted as the far infrared, and those two numbers don't seem to quite add up yet. There seems to be about a factor 2 off, and a factor 2 in astronomy is still something to worry about. We like to be exact, and especially these things tend to add up over distance. So it's important to figure out which one of these kinds of dust is dominant.
The most well-studied dust ring around a star ever. And then somebody widened the field of view and realized there was a 1,000 AU dust belt around it. They have been looking at these things with the kind of wavelengths to see dust for a decade, and they missed a 1,000 AU dust belt out around it. We are not good at seeing this stuff at all. This one was published in the Astrophysical Journal. It is official, what many people have thought and hypothesized. There is a widespread presence of nanometer-sized dust grains in the interstellar medium of galaxies.
The structure, especially in the interstellar matter, seems to be very self-similar. So if we look at the largest scales, it looks pretty smooth. But as soon as we look in any kind of detail, it breaks up into filaments, and those filaments break into filaments, and those filaments break into filaments.
SOFIA. They did spend a lot of money on SOFIA. It was supposed to help solidify this force of gravity model for the formation of stars and star clusters. They found out that not only are magnetic fields and turbulence, and when you see turbulence in this realm, they're talking about plasma turbulence, plasma interacting with itself and interacting with electric and magnetic fields, not what many of you might have experienced on the flight here into the rain and clouds yesterday. But so magnetic fields and plasma turbulence are not only involved, they may dominate the creation process of these stars and star clusters. The missing mass of the universe is tracing the cosmic filaments. Now, this is where mainstream scientists say, okay, but that was just the normal matter we knew was missing. We still have all this other stuff we need to look for. The problem is, finding all of the missing matter scattered about is very different than finding it in a current. And we know that these cosmic filaments feed material down onto galaxies. So when you have all this material and it's not spread out, it's actually in the cosmic filaments. It's traveling the same direction, feeding galaxies. It is a current. There are magnetic fields wrapped around it. They see protons, they see electrons in these things. And so matter is no longer just matter when it's in a current. Okay, if it's spread out everywhere, it has its gravitational attraction. If it's in a filament, it has its gravitational attraction, but it's got a lot more than that, doesn't it? It's creating magnetic fields, it's creating electric fields. And that way, a baryon, a proton, is no longer just a proton. It's now doing a lot more, and it's affecting a lot more. Okay, well, if we have these, if this really is a whole magnetic mess, then we should be really seeing these with every little structure. And so what you see here, when you see a blue circle, that means the magnetic fields are wrapping towards you. Red means they are wrapping away from you. And you should see the white filaments in the middle of them. Every single one they've looked at, there must be a current hidden that they cannot see running through the filament because the magnetic fields are uniform and wrapping around it, just like you'd have a magnetic field wrapping around electricity going through a wire. Now, they can't see the electricity going through these filaments, but it must be there. Otherwise, the magnetic fields would not be uniformly wrapping around it like this. So, probably the most incredible filament of all isn't a filament, it's a sheet. So the Musca filament was one of the brightest filaments in our galaxy that we can see, but it turns out we're just looking at it edge on, and it is actually a flat sheet. In the bottom right picture, I have a bunch of colored lines drawn. They are all magnetic field directions, but what you'll notice is the green ones are all of the filaments that are coming off of a main cloud. The main cloud would be in the top left part with the large blue line running at a slight angle. And then down towards the bottom of the extended filaments, you can see that those filaments have their own filaments coming off, again, at 90-degree angles. Not only are all of the filaments that they're seeing have the magnetic fields either wrapped around them or embedded in the length of the filament, but when they're coming off of a larger cloud, they're all perpendicular to one another. This is the right-hand rule of electromagnetism. That's why they're forming where they're forming. And so this is that little blue pink thing up at the top there. That's what they believe the Musca filament, Musca sheet actually would look like over on the left. If you could take it and turn it so you could actually look at it sideways, it's a flat sheet. And the icing on the cake, those little white things, those are other magnetic fields. So they not only notice the magnetic field cutting through the sheet of Musca, but there's perpendicular magnetic fields all throughout it as well. This is a 100% electric structure. There's no way for gravity to do these things. When Sophia comes out and says that stars and star clusters are about magnetic fields and plasma turbulence, the predecessor of a star cluster are these molecular clouds. These are the someday to be nurseries of stars, or so we think. And so there's no way for gravity to set this up where not only do the magnetic fields trace all the filaments, but they're all perpendicular to one another. It's mainstream in the sense that that's the right-hand rule of electromagnetism. It's not mainstream in the sense that that's not supposed to happen out in space. That's not what's supposed to be dominating out in space. It's supposed to just be gravity, random collapse, chaos, things like that, and it's just not the case.
In 2018, a NASA article, basically out of nowhere, mentions our existence in the plasma universe, which was a baffling sight to see for those of us who know how many plasma universe physicists don't think dark matter exists. One of the projects that has received very little attention and which we really don't hear much about is poised to be the next leap forward in our understanding of the real dynamics of cosmological constituents.
I'm Anthony Peratt from Los Alamos National Laboratory, U.S. Department of Energy. I started out in plasma cosmology under the Nobel laureate Hannes Alfvén. Alfvén had written a book in Swedish called Cosmic Plasma. Well, I know something about Swedish and certainly I know something about English. So I wrote the first English edition of Cosmic Plasma under Hannes Alfvén's name. One of my fortes was supercomputer computing of large-scale matter. So for 12 years we did teraflop computing, the full set of Maxwell's equations on matter, electrons, ions, and neutrals, wholly three-dimensional. In other words, real-world calculations. And from that we were able to, much to our surprise, calculate the full evolution of plasma and neutrals acting under gravitation, plasma acting under electromagnetic forces, and recover the evolution of plasma collected in the universe as it evolved towards a galaxy and eventually a spiral galaxy.
Alfvén, Peratt, Birkeland, the three founding fathers of the plasma universe. If there is an accretion of the intergalactic medium in those regions, meaning outside of the galaxies, then the orbital velocities of neutral hydrogen clouds are determined not only by the gravitation of mass inside their orbits, meaning that if you have a bunch of stuff where we think there's empty space outside of the galaxy, if it's there, I know we can't see it, and most astronomers don't think it's there, but if it just happens to be there and we can't see it, the math says you don't need dark matter anymore. And I'm going to go back up here. This is what Christian Birkeland said. We have assumed that each stellar system in evolutions throws off electric corpuscles into space. It does not seem unreasonable, therefore, to think that the greater part of the material masses in the universe is found not in the solar systems or nebula, but out in the empty space. What we didn't know is that the active plasma nucleus, supermassive black hole, whatever you want to call these things at the centers of galaxies, they are feasting on many more stars than we realized. And in addition to feasting on many more stars than we realized, they are blowing out an enormous fraction of that which they take in, up to 80%. So this whole stuff is getting eaten by the black hole? No. A lot of it's getting shot out the cosmic jets, and a lot of it is getting blasted out. Well, here's the thing. We know for a fact from the observations that the stars are going in. We know for a fact that the material is getting blasted back out, but they look in the inner galaxy and that plasma's not there. They look in the spiral arms and that plasma's not there. It's been blasting out from the center of the galaxy for billions of years, but they don't see it in the middle. Where must it be? It must be around the galaxy. There's nowhere else it could be. Now, that's some pretty impressive circumstantial evidence, but it's still just circumstantial at this point. So let's see if we can gather up some more real evidence for that material being out there. Well, you remember this? The most well-studied dust ring around a star ever. And then somebody widened the field of view and realized there was 1,000 AU dust belt around it. There is a widespread presence of nanometer-sized dust grains in the interstellar medium of galaxies. We're going to come back to that in just a minute. Because this is when the whole thing should have fallen apart. Does anybody know what you're looking at here? Do you remember this is just a couple of weeks ago, the lost light of Hubble? The white areas on here, that's areas where they still have no return. Just looks like black empty space as far as you can see. The colored areas are the galaxies that they know. The black areas around them are the dust and gases and other things that they knew of. The gray stuff around those is the lost light of Hubble. So around all of these galaxies, where they could not see before, is a whole bunch of dusty plasma, a whole bunch of emitting sources exactly where They were predicted to be by the plasma universe and in the place where, mathematically, dark matter dies. But getting into this dusty plasma and why this is so problematic for cosmology, because it is a trickster. It really is. And so I'm just going to read some of the stuff up here. When they were doing these experiments with dust on the International Space Station, there was not chaos, but they noticed order imparted on the dust. It lined up, it formed waves, it formed crystalline structures. Now, they determined that these crystalline structures and the lines and the waves were based on electric fields. That's how they were lining up. It wasn't based on gravity. And so when you have these regions around the Earth, around the solar system, around the galaxy, interacting with electric fields, forming these crystal patterns of dusty plasma, it basically means we are looking at the cosmos through a kaleidoscope.
The national labs have been gaining traction in these plasma universe discussions. In the weeks just following Sophia's magnetic and plasma discoveries in star-forming regions, SLAC showed it was the magnetic fields powering cosmic jets, not a function of the accretion disk energy. And then Lawrence Livermore at Berkeley saw electric currents driving those field actions. Their torus jet modeling mirrors what we see across the country at Princeton's Plasma Physics Lab and their NASA collaborations. There's that recent Navy patent as well for a super technology using plasma magnetohydrodynamics, and expressly states in the patent the device works because we live in a plasma universe. So we have now arrived at this weirdest possible point in physics, haven't we? Grant money and university professors mostly chasing dark matter, along with the popular media articles, while some NASA teams in the National Plasma Labs are all seeming to be chasing something else.
They can't seem to get the correct results, and they seem to think it's due to some magic essence that they have left out, and they call it dark matter. So as a result, you have several hundred professors, graduate students that are working towards their PhDs somewhat, that are pursuing dark matter without any knowledge of what it is. There's no missing matter at all. We just had a lot of experimental data that we could compare the simulations to at energy densities that universities, graduate students, professors, associate professors, full professors, professors emeritus simply did not have access to. We did. Now, the universities really, and I had a choice once I had a PhD. I could go into a university and get tenure eventually, or I could go into a national laboratory and work with real data, real equipment. My gosh, the equipment that we burned up in the first millisecond of a nuclear explosion underground was just more than all of the universities in the world could afford. They simply can't afford that, to lose that kind of that investment in high power, sophisticated measuring equipment so quickly. And plus, you're working in an environment where you're working with real world physics, not the physics that you learn in textbooks, that maybe 5 years old, 10 years old, 200 years old. This is real world stuff.
Next, we wonder about the 3D simulations that they do have now, and one of the most renowned is Illustris. The problem is that the mistakes that drove matter physics into darkness have progressed far more quickly than the reduction in price of supercomputing. And what this means, practically, is that since the universities attained the ability to work with this level of computing, they have included dark matter and dark energy to a degree dwarfing the luminous matter, and have lacked the luminous matter being discovered by the weak, the dust, the plasma, connecting galaxy clusters and clusters to the cosmic web, surrounding the galaxies and controlling star-forming regions. The natural extension of these discoveries is the electrical action at various scales throughout the universe.
Let's say I burn toast in my house, and I mean really burn it. I put it all the way up, I smell it burning, I see the smoke, and then I just kind of like turn my back and I let it go for a few more minutes. Then let's say I eat the piece of toast anyway, because that's how I like toast, and then I take the toaster and I throw it out the window. Then I bring you into the room and I say, find the source of that smell. You have no chance, because I've eaten the toast, I've thrown the toaster out the window, all the evidence is pretty much gone. All the evidence you'd want to really understand it. And that's what we're talking about with a potentially extinct current here. Something caused these filaments, and it wasn't gravity, to form like this, like lightning throughout space. And that thing really might not be there anymore. We might just be seeing the aftermath. The smoke trail from the meteorite that blew up 4 or 5 seconds earlier, and there's no more light from it. It's just the essence of it. It's the smell of the burnt toast that's left over. And so now we come back to a story that I think most of you probably know about. They flew Cassini through the water jets, the South Pole of Enceladus. Magnetometer, hot and running. Langmuir probe, hot and running. They detected phenomenal magnetic fields and only 5% of the requisite electric current. So that is a satellite flying through the electric current. We call that in situ measurement. And it detected 5% of the electric current. This is important for 2 reasons. One, if we can fly right through it and only detect 5% of the current, we see nothing from Earth. Looking out into the cosmos thinking, oh, well, we don't see these electric currents in the cosmos. No kidding. Good luck seeing them if you spotted 5% in situ. But the explanation for why it was hidden, the charged particles of the current were actually being attracted to and hidden by dusty plasma. The dust was actually hiding the ions. The reason they were not able to see the current of charged material in the cosmic web was because of the dust. The exact same thing they ran into in Enceladus. And not a single astrophysicist or cosmologist has put these two together. The same problem that they ran into at Enceladus should have given them a clue about how pitifully they see electric currents in deep space. They have already run into with the cosmic web. Oh, well, that's where the normal matter is flowing in that current. We just didn't see it because of the dust that was surrounding it. It's right there. It's right there on a plate. We have a number of new models of the galaxy that have come out just this year. And I've spoken to some of these folks. Some of these folks definitely know the plasma cosmology individuals. These are some of the models that are based on what came out of either one of the national labs. This is what they say we're looking at. And obviously on the right there, we're looking straight down through the axis of the cosmic jet. But they say this is what's actually in the center of the galaxies there. The number one model that's coming out is this torus jet model. Regardless of whether or not it's a black hole, a plasma nucleus, what's around it is a torus and a jet. We don't know what's down there at the exact center. People have a lot of good guesses. But what's just outside of it is observationally undeniable. It's a torus and a jet. And this is what you get when you have that energetic point. And so in the image on the far left where you can really see the jet going up and down and the torus around it, you can't see the full Z-pinch there of everything coming into the middle with the torus wrapped around the waist of the Z-pinch, so to speak. But that's what we've got there. And they fade as they go up because they're losing energy. It's more dark mode rather than glow mode plasma as you get way, way out there, and specifically as it starts to arch back around and make the larger torus. But you can see the interior of the torus here, and this is Billy's first try over there on the right, just doing the fundamentals and turning on the power. He created the jet torus model right there before our eyes.
After the 2019 Observing the Frontier conference, the months that followed brought with them a flood of discoveries, illuminating the pathway forward. Sophia continued her charge, demonstrating that magnetic fields are responsible for action at larger scales, all while Alma confirmed Sophia's previous discovery about the importance of those magnetic fields in smaller star-forming regions. We began to see genuine attempts at scaling up these principles to cosmological scale, and we're seeing those published in major physics journals. Plasma universe, magnetic universe, electrodynamic universe. Coulomb is just another way to say it. At the galactic level, we're seeing tremendous advances in magnetic modeling of a large-scale coherent structure and pattern. This is opposed to the random, chaotic, nova-driven field paradigm that operated for years. The regions between the galaxies and the cosmic web were the final remaining piece of the puzzle. The missing matter is still being discovered at an incredible rate, still just hiding in plain sight. Just outside the galaxies, they discovered that all the material outside the visible stars is co-rotating with the galaxies, indicating that the galactic rotation problem may disappear entirely with more observation. And how that material gets to the galaxies is even more amazing. They come in filaments, currents, moving in a helical vortex, spiraling down onto the galaxies directly from the larger filaments of the cosmic web. That is electromagnetic action, not random chaotic gravity. And so to summarize where we've already discovered the dominance of electromagnetism and luminous matter. It's the star-forming regions and the star-forming rates, the molecular cloud structures, the dusty filaments, active galactic nuclei and their electric current and magnetic field torus jet model, with the luminous matter surrounding the galaxies, with how it rotates, with how it gets to the galaxies in the first place, and with that largest scale structure, the cosmic web. Well, and right, this is the appropriate question at this point. This is actually about the time when the more seasoned professors began to remember Alfvén Klein cosmology, the predecessor to the plasma cosmology that Dr. Peratt is talking about and we're all talking about. And even though it is a bit different, a man named Jim Peebles in 1993 basically thwarted the charge of what they called the plasma dissidence to supersymmetry, dark matter, basically looking at non-luminous matter, things like that. And the two problems were that with Alfvén's initial models, there were some disagreements with the cosmic microwave background. We've heard a couple of things about that already here, haven't we? But also, and more importantly, there were these missing high-energy photons from annihilation events in the cosmos. And, well, we've seen they're not really missing anymore. It seems that we keep having to report these super high-energy photons that are breaking records for the detections. And so it really is a different situation now than back in 1993, especially since we're learning that there are some tensions, Hubble, Planck, expansion, cosmic microwave background. We really do need to get these new instruments up there and see exactly what they're able to tell us about the universe at a large scale. And you know, speaking of the larger scale on this, you know, Dr. Peratt's open letter to the scientific community now has dozens of signatories from the field, dozens more in related science and research fields. It's not shocking that the national labs do seem to be nailing it. There are a number of people on that signatories list that are from the national labs. It's not shocking that Peratt did it in Los Alamos. It is, as you said earlier, it is just a shame that his work had to be classified due to the nuclear connections.
I might add that this is a very exciting time to be in physics and to be in the field of astronomy, and by astronomy I mean astrophysical plasmas, because so much data is pouring in now that is providing justification, which we already knew because we'd done the large-scale experiments. It's the physics, the high-energy density physics that you're allowed to get into going into the national laboratories. And this is void in the universities. Name a university and they simply do not have the funds, they do not have the equipment. They can't do high-energy density work as is required when you're looking at the universe. The universe is the biggest pulse power generator we have and the largest high-energy density media that we can experiment with. So all they're left with is ignorance. And for that reason, a large majority have gone to dark matter, invisible matter, missing matter, ghost matter, so on, to explain the failures of their codes. They publish a good many papers, and really, university physics is about publishing papers, be it right or be it wrong. And in most cases, especially with missing matter, it's wrong.
Unfortunately, the situation is even less rosy than the picture painted by Dr. Peratt. I conducted the interviews for this infomentary, a dozen others that didn't make this infomentary, and there were numerous other interactions via phone, Skype, email, even in person, with no less than 95 of the professors currently teaching these topics to today's youth in the United States, Canada, Australia, and Europe. There was a disturbing trend that I seemed to notice as I was talking to professor after professor, and many of them were not shy at all about admitting this. They are grossly incapable of keeping up with all of the science that is coming out that might potentially affect their field, might potentially affect their work. Now, there are 3 reasons why this is the case. First, professors are busy. In addition to any research or paper publishing or experiments they might be doing, they probably have to teach classes. They have to grade papers. They have to grade tests. And there's also an enormous amount of administrative work that goes into the individual students, the department, and the university as a whole. Second, this is actually not one field, but many fields rolled into one. Astronomy, astrophysics, astrophysics of galaxies and galactic dynamics, magnetic fields, plasma turbulence, large-scale cosmology, dark matter, black holes, nebula, gaseous and dusty star-forming regions and their interplay all together, each one a very specific and highly specialized field of science. What it takes to be a player, publishing in just one of them, pretty much boggles the mind. It's very difficult to keep up with many high-level fields of science. And that brings us to number 3, which is the one that most of them identified themselves as being the major problem. There are so many places where this information is coming out, and there are just only so many hours in the day. The Astronomical Journal, the Astrophysical Journal, Astronomy and Astrophysics, the Astrophysical Journal Letters, monthly notices of the Royal Astronomical Society, Nature, Nature Astronomy, Physics of the Dark Universe, Physical Review D, and Cornell's preprint archive, 5 days a week. We're talking about 50, 100, sometimes 200 new papers a day. And they're not all going to be relevant, but you have to scan through all of them. And a good dozen to 3 dozen probably are relevant. It's just not possible to keep up with all of those other things when you have a professorship, when you're doing your own research, leading your own research, when you have all those other responsibilities. It really does require a full-time, dedicated passion for keeping up with all of these material. And the interesting thing is most of them have the passion. They just don't have the time.
Fluorescent dyes to attach to
is Michael Parrish, also from Sapphire, and he's going to be the main director.
One of my jobs on the Sapphire team is to suggest specific experiments we can do in the lab that can be correlated with satellite and telescope data. In this second talk, I'd like to give you an idea of how I engage in that process.
Temperature 310-6. Okay, so now you can go into... Okay.
Here's Montgomery Childs introducing hydrogen into the chamber, which produces this, a plasma double layer. A score of instruments take readings in and around the Sapphire plasma engine. The data is fed to computers in our control room, where it is collected, synchronized, and cataloged, to be later analyzed and used in writing papers. These are pages from one of Lowell Morgan's papers and pages from one of Montgomery Childs' papers. At the moment, the team has 4 additional papers in the works describing and explaining results of our experiments with the Sapphire plasma engine. Sapphire's mandate is to generate and record events and to collect, analyze, and disseminate data.
We want to bring it up to 3 torr.
To this end, Sapphire has a core team, a review board, and special consultants. Everyone is constantly on watch to maintain a clear demarcation between the theoretical and the empirical, and to make sure Sapphire adheres to the strictest discipline in experimentation and data recording. I believe any lasting contribution of the Sapphire project is going to be in its raw data and hard empirical evidence. Correlating the data from Sapphire with the latest data from deep space is not as straightforward as it might sound. The Herschel and Planck millimeter telescopes have sent back new images of our galaxy's interstellar medium that have many in the astronomical community reeling. It is as if you're riding along and someone pulls a wheel off your bicycle. We are struggling to make sense of this data. It simply does not fit with our previous theories. The previous theories need to be abandoned or severely modified. I think we might need new models. Empirical science requires rigorous adherence to strict rules of process and discovery. Developing new models requires a certain freedom of thought imagination, even speculation, or going deeply into other disciplines to help spark some new insight. This second talk is to offer you a few examples of ways I have sought to understand new astronomical data and to explore the possibility of new models.
We are at a very exciting time in astronomy. If all goes well, our children's children will say things like, "Oh, I wish I was there at the beginning of the 21st century when astronomy was being rewritten. What was that like?" Many of astronomers' pet theories like dark matter and black holes are headed for the dustbins. And this is partly because of new data coming back from the interstellar medium, from the Herschel and Planck telescopes. As we collect more and more data from ever more awesome telescopes, there's a notable confusion if we are looking at biological images or astronomical images. One of these is a micrograph of a cell. One of these is new data from the interstellar medium. Same. One from the interstellar medium, one from the world of cells. Same thing, interstellar medium, world of cells. This is my favorite. Two of those are from the world of biology, two are views of something going on in our galaxy. So this is not an accident that they look the same, and it's not an artifact of our instruments. The reason these two worlds look so similar is because in many ways they are similar. We live in a living universe. The cosmology that we grew up with is dead. And I don't mean dead as in over with. I mean it only talks about dead things. Stars are supposedly dead. Galaxies are supposedly dead. The whole universe is supposedly dead. And only you and I are alive. Only you and I. The profoundness of this absurdity needs to be re-examined. Astrophysics will be stuck until it can acknowledge that the objects it studies are alive, just like you and me, and our little cells. I knew my cells were alive before anybody showed me a movie of it. I also know that stars and galaxies are alive before anybody shows me a movie of it. That's mitosis, cellular division. When I was looking at the left-hand one, I just happened to see the right-hand one in somebody's astronomical catalog, and I'm like, where have I seen that before? This is an image of an animal cell, and it's what you would see with your eyes, with visible light. And when I was young, I was told that all those little functional pieces, mitochondria and the Golgi apparatus and the lysosomes and all those functional pieces, I was told that they float around randomly in an unorganized sack of water. And it was assumed that random purposeless motions were somehow accomplishing all the required millions of complex biochemical reactions for cellular life. For example, if new amino acids came in from the right-hand side of the cell, but they were needed on the left-hand side to do something, that somehow they would just meander over to where they are needed. And it was actually known that random diffusion was about 1 million times too slow to account for the speed of biochemical reactions, but it was forbidden to propose any model where the cell actually knew what it was doing and why it was doing it. Then, in the 90s, we developed fluorescent dyes to attach to a different set of biological molecules than we could see before, and that's what the cell looked like. I was in graduate school when this work was being done at a different place, and everybody is like, what are we looking at, right? And then after just a few years of research, we uncovered that these different filaments on the right-hand side, they're actually holding together all the pieces of the cell and moving all the pieces of the cell around. And by watching further, we could see that raw materials like amino acids or whatnot, when they're brought into the cells, they're packaged together and they are brought to where they are needed by the cell. And so this is an example, computer animation. But I remember vividly when we started to see the movies that this is based upon, the data, and it just changed everything about how we understand how cells work. So in other words, the entire description of life at the cellular level was turned on its head, and what was assumed to be random and purposeless, we could now see was a carefully orchestrated and purposeful activity. And just to be clear, the old view that cells could function through random motions of molecules, that theory was never proven, and in fact, all the evidence we had said that it couldn't actually work. But the random model was vigorously defended for years since, well, it's assumed we live in a random, purposeless universe. And it took the invention of new microscopic techniques for the diffusion model to be proven false. In other words, we had to see it with our own eyes. Now, we can only build models from what we see. And for example, if we could only see our bones, so say we couldn't see our viscera or our muscles, then we would say things like, oh, there's a lot of empty space in the human body. And we would say that the bones move around because of random air currents and crashing into other bones. But if we can see muscles, then we can develop models where we say that the bones are being moved by the muscles for the purpose of moving the body about. This is an image that we're all familiar with. It's what we see with our eyes when we point a telescope at the night sky. We see one point of light, then a lot of empty space, and then another point of light, and a lot more empty space. And since this is all that we saw, modern astronomy built its models upon this picture. I recall one assignment in school where we had to take the known distances between stars and the known sizes of stars, and we had to prove that it was impossible that two stars could ever come close enough to touch each other. And I used to hate those assignments where you had to prove we live in a disconnected universe. And you still hear this way of talking. Recently listening to a radio interview of a prominent astronomer, and she's using phrases like out there in the darkness and the unimaginable expanses of empty space. Let's look at the similar region of the sky, but with the new data that we're getting back from the telescopes. So it seems like we have a complete reversal. The new data is showing us that most, if not all, stars are connected to other stars, and that a lonely, disconnected star must be more the exception than the rule. All of modern astronomy was built upon the left-hand image of disconnection, and we can only create models from what we can see. And now our current model needs to be amended, and the rewriting is taking place right now, which is very exciting. So what are we looking at with those filaments? It's important to say that we don't know. No one really knows. This is new data. And like any other data we get from any telescope, it's partial. It's only showing us a narrow slit of what's really out there. Now, that being said, we are pretty confident that these filaments are made of silicates, dust silicates, finely powdered rock. But we also see large quantities of hydrocarbons, sugars, and amino acids. Right, hydrocarbons, sugars, amino acids. Up until a few years ago, these substances were thought to only be found on the surface of our little disconnected Earth, right? So what are they doing up there connecting billions of stars in a galaxy? Many publications you read refer to the filaments as regions of star formation. That might be true, but that description assumes that the ultimate goal of any matter in a galaxy is the creation of what we call a star. Saying that these are stellar nurseries assumes that the filaments are there for the stars, but maybe the stars are there for the filaments. Or maybe they're both there for each other, or for something larger. So as we get more and more data from these structures in the interstellar medium, I suggest we hold off on rushing to conclusions about what it is we're seeing, and keep an open mind about the larger picture that's opening up. Since I often look at the electrical aspects of stars and planets, I wondered if we might be able to see any electrical discharges in space, lightning bolts in space. And one of my colleagues, Ignacio Cisneros, he's teaching me how to do multi-wavelength astronomy, overlaying different regions of the sky. Great man. And so this is a picture of the one region in the sky. There's about 50 years, maybe it's 40 years, separating the two images, okay? So what is this discharge? We don't really know. No one knows what these are. Are there a lot of these? Yes. In about an hour, he showed me a dozen such examples as this. How long does it last? We don't know. How much energy is released? We don't know. They are out there. The trouble is that no one's been looking for them. I mean, even something like the Gaia telescope project, which is awesome, but it's only looking at changes of point sources. That's the design. So to look at changes of diffuse discharge like this, that's going to take some new work. I think that most astrophysics is floundering with data overload because there's no thought that we are looking at structures that are performing useful functions. What is the function of those filaments in the stars? What is the function of those transient discharges? More data will not necessarily help if we're not asking the right questions. I think that modern cosmology took an unfortunate turn several hundred years ago by denying or ignoring the question of function or purpose in the larger cosmos. Biologists recognize the principle that form follows function. So why do astrophysicists not recognize this principle? Why are astrophysicists not asking this question? The idea that life or intelligence would be attached to a planet or a star was too much for our consciousness, so we denied its possibility. There was never any evidence to substantiate that denial, and I don't need to tell the people in this room that denying a star could be alive is a misuse of the scientific method. In the last 2 generations, we've developed telescopes to show us galaxies, billions of galaxies, trillions of stars, and then we promptly declared them all dead and having no purpose to themselves or to anything else. I would propose that blindness of ours can in a large part be explained by the limitations of our perceptions. Each of us, each person on Earth lives for about 80 years and can only directly perceive several miles of his or her surroundings. Galaxies exist for tens of billions of years and are so large that it takes light 100,000 years to go from one side to the other. So what can we possibly directly perceive about a galaxy, given this almost unfathomable difference in our duration and size? If you work through the numbers, each of us stands in relation to our galaxy as a single electron stands to your body. So imagine that each of us is an electron within a molecule, within a blood cell, somewhere in a human body. And further imagine that your whole electron life comes and goes in a millionth of a second. I lost page 10. Interesting.
It's the universe wanting you to improvise.
So each of our lives goes, her whole life, my whole life, millionth of a second in this analogy I'm creating. And then all of human history, all of known history would pass by in a thousandth of a millionth of a second, right? So what do you think such electron astronomers as us in that scenario would be able to directly perceive about the human body? I'm not saying that the electron astronomers would get the physics wrong. I'm saying, would they understand what they're seeing? So we astronomers are handicapped in just such a way when we try to study stars and galaxies. We live in a world that is part of a much larger world, that is itself part of an even larger world, and we have within us smaller worlds made of still smaller worlds. And to know these worlds as they appear to themselves requires that we change our perceptions and probably also change the quality of our emotions. When I make an effort to directly perceive the sun or the earth, I notice a subtle shift, whether I'm in a place of gratitude towards the sun and the earth. To overcome these limitations of perception, more data alone will not necessarily lead to a deeper understanding. Another new telescope will not all by itself elevate our perceptions and feelings. We should also ask, how do I elevate my perceptions, my feelings, my senses? Many of us have had at least moments of elevated perception. That's why a lot of us became scientists in the first place. So if any of you would like to discuss this further, come find me. Happy to talk.
So here we are. I want to thank Lucy and Adrian for inviting us. What we do is empirical science. We're not theoretical physicists, although we do use a lot of theoretical math to develop and design and build SAPPHIRE. The purpose of SAPPHIRE is to test the electric sun, the electric universe model. Back in 2011, I was approached by folks out of at the time, the electric universe, the electric sun community, to see if there would be a way to test it. And I did an evaluation, and we're going to be talking quite a bit about what's called design of experiments, but it's a methodology by which you can filter a hypothesis to see if it's testable. And so that's what happened. SAPPHIRE got started in 2013. It has proven that it's capable to contain, control, and stabilize high-energy, dense plasma. We're seeing chemistry changes. We're slowing the speed of light. Variations in electron density comparable to the photosphere, the heliosphere, and nuclear bombs. Electrical confinement of high-energy photons, when you break the model down, it's due to charged plasma affecting matter of a different electrical potential, and that's it. It doesn't mean that there isn't other factors, but those are the two primary factors, and it looks like it's testable. So the research objectives. SAPPHIRE stands for Stellar Atmospheric Function in Regulation Experiment, Testing the Electric Universe in the Electric Sun Model. We have one peer-reviewed paper that was published a year and a half ago, I guess. It's a study of striations in a spherically symmetric hydrogen discharge. And what we discovered is that in these double layers that you saw in the video, inside these, it's trapping electrons and ions. We call them plasma wells, or we call them double layers. In those double layers where that matter is actually being contained. It's actually sequestering material into the core just above the surface of the anode. We have 4 other papers that we're working on. We may get them submitted for publication this year, I hope. A lot of work to do. So the technology in SAPPHIRE. These are just a few of the things that we're measuring in SAPPHIRE. So it's like a super instrument. It's not like it's an apparatus and we're just firing it up. We have a variety of different instrumentation that we measure in real time. And then you'll see later on, after we do those measurements, we collect the data in real time. We're working on doing an overlay of the data in real time. So mass spectroscopy, optical spectroscopy, oscilloscope readings, RF, are getting recorded, and then we place them over top of each other to give us a real-time indication of these measurements as they relate to each other. Okay? This is not really, I don't know that it's ever been done before. I mean, maybe a couple of things, but a couple of instruments, but not to this degree. And then we have post-experimental analysis that we do as well, and we'll be getting into that. So we have the plasma itself where we contain it, control it, and then measure it in real time. We collect the data back, do analysis on that data, but we also take other data or other items like the anode and send it out for post-experimental analysis. Optical spectroscopy.
Optical spectroscopy is one of our methods for analyzing what's going on in the chamber. What you're seeing here is 3 different settings or intensities of the discharge. The anode there is the center glowing ball. And then we place fiber optics to take in primarily visible, but a little bit into the IR and UV also, light. You can see in this case, the fiber is placed inside of one of those striations. The next one, we point it away from any striations, so just into the side, if you will, of the discharge. And then in this last one, we turned all the dials up to 11 and got the most we could and measured the light coming from that discharge. And what we're focused on, often with the optical spectroscopy, is the width of the line. So light, as we know, is in colors. A lot of times for optical spectroscopy, we're looking at just one color, one emission line from a substance, an atom, a molecule. This is a sort of data we see from our spectrometer. This is the intensity of the light as a function of wavelength, and you can see it's centered on about 656. That's a very famous hydrogen emission line, and it has a certain width to it. We look at the second case where we move the optical fiber a little bit off to the side. We do the same measurement. We see there's a different width to the line. And then the third case, again, same measurement, a different width for there. The width can tell us a lot of things about what's going on in there. The width of spectral lines is one of the main ways that astronomers use to measure temperature in the sun, in the corona, in the chromosphere. There's other methods also, but this is one of the main methods. And one of my jobs for SAPPHIRE is to take whatever methodologies are being used by NASA and ESA and use the same methodologies in our chamber. So to speak, we can do apples to apples in the comparison. If I showed this data to a solar physicist, he would interpret it as temperature readings or of electron density variations. I won't go into how you would distinguish the two right now. We're going to look at the electron density variation aspect of what these lines are telling us. So those changes in the line widths, this width is 0.12 nanometers, which means we have a very fine resolution in our chamber. The width of this 0.07, 0.09 nanometers. What do those mean when you work back as a solar physicist would, and you say, well, let's look at the electron densities that those are showing us.
And that variation of just 0.05 nanometers in the line width means that we have variations of electron density in our chamber at 50 to 100 times. We don't know the absolute value from these numbers, but we know how much it's changing, how much the variation is. And within those 3 different discharges that we showed you, that variation in electron density, 100-fold variation in that density. Well, this was very exciting for us because that's one of the main difficulties in explaining the photosphere electrically, is how would you reproduce that size of electron density variations? We didn't know we were going to get this, right? We had no idea. But those density variations are exactly what one sees in the free electron variations off the photosphere. Voyager going through the heliosphere sees similar variations in free electron density. So again, this is all in line of us reproducing astronomical observations, thank you, in our chamber.
Okay. The reason why we're a little bit, it's different is because, well, we don't have Paul here.
I know.
Now I have to start talking for Paul, and Paul's different.
Yeah.
Paul and I have, he does engineering, I've done a lot of engineering, he's a chemist, I'm a mechanical guy. Don Scott's a sparky, I'm a cranky, so we. In any case, so Paul's not here. I'm going to attempt over the next bit here to explain what a design of experiments is, how they're used. And to date, I don't think we've been super successful. Well, we'll try, and then you can give me some feedback afterwards to see whether or not we've been successful. Okay? This is just a nice, cool little video to give you an indication of the control that we have over the cathodes. Okay, so this is sapphire. Complicated. The chambers are quite large. We could fit probably 10 people, maybe 8 people comfortably, maybe 10 people inside the chamber. Looks like kind of a jet engine, and in a way that once we fire it up to keep the chamber cool, because of the temperatures that we're seeing, and we'll talk about that. The fan at the back itself will do 14,000 cubic feet of air per minute. So this is SAFCON. That's Yano. He's one of our techs. What you're looking at around inside SAFCON here, we haven't got them all listed, but we'll try to give you an idea of what's going on. We call it SAFCON because we said we're going to call it the office, we're going to call it the control room, and one guy said, well, it's Sapphire, and somebody said it's control room, so we just call it SAFCON. Sounds cool, we think, anyway. So a 5-region high-resolution optical spectroscopy, which is what Michael was talking about. So Sapphire has the capability of measuring 5 different regions within the plasma. So we have 2 long probes that come in. We can move them around in 3D anywhere in the plasma. We can put them right into the double layers, move them over in different regions, but 5 different regions at the same time. And it measures at a rate of a megahertz. That means basically a million measures, that's per minute, right?
Second?
Per second, right. That's right, I'm sorry. Well, let's do the math. So that's per second, so a million measurements per second. So we can pick up change in the optical spectroscopy very quickly. It's very sensitive. Data transformation. That's what I was talking about. We can do overlays of all the data. So we collect it all, goes into one computer system, and then we start to do overlays of the data graphically. So what you can, if you look at numbers like me, I can't make sense of numbers. But if I look at a graph, we can start to relate to it. Live lab stereo camera, just in case somebody's out there, but it's safety, but it's also it gives us an opportunity to see some of the manipulation. It's not, when we're running Sapphire, nobody's allowed out in the chamber area. So real-time ultraviolet light measurement, infrared. We do that to monitor, well, temperature, of course. The next one is Sapphire supervisory control and data acquisition, SCADA. That'll probably be new to many of you, but it allows us to gather the data back from what's going on in the chamber. We have already got pre-settings, you might say, as to how we want the chamber to run. So it's supervisory control, which means that the computers themselves can control, let's say, pressure, as an example, or vacuum, okay? And so we set the vacuum to be a certain pressure, and using cool technology like servo motors and butterfly valves and that, computers can maintain the pressure and the vacuum within the chamber. 6-region mass spectrometer. Okay, so the mass spectrometer as well, we can go in and the mass spectrometer is on the 2 probes with the optical spectrometer, so we have both optical, mass, and Langmuir probe in one probe. So we're measuring all 3 at once. And we can move it anywhere into the chamber. We're looking for any chemistry changes. And, well, Langmuir probes, as Don pointed out, are used to measure, the E field plus a lot of other things. And it tells us a lot about what's going on in the plasma. And Michael's going to get into the analysis, which is pretty amazing stuff. So radio frequency, many more things, but that's SAFCON. I think we have 15 computers in there, servers, some of them are monsters. There's a lot of data to process. This is an overview, anode extraction, and this allows us to take the anode out of the chamber without compromising the chamber gas. It takes a long time to purify a chamber like this. So it might take 2 or 3 days sometimes to get us so we get all the impurities out of it. So this is an isolation chamber. You see it in spaceships as an example. Before you can actually walk in, expose them, we have valves in there that shut it or open. We pull the anode out, we shut it. We can change the anode or change different things. Then we close it back up, evacuate it, and then we can put it back in the chamber. It allows us to do a lot of different experiments very quickly. Okay? Of course, vacuum pumps, because you need vacuum pumps to get vacuum. Cryogenic, air cooling, chiller. The reason why I have a chiller is because we actually cool the core. So we use deionized water, which doesn't conduct electricity, and we pump it up through the core and some of the anodes and the hollow ones, so we can cool them down so they don't melt, okay? Mass spectrometer remote, gimbal, and chamber door. Well, we have a big chamber door we can open up and get in. This is just a basic circuit here. It gives you an idea of the gas and vacuum control. Okay, now I don't expect you to understand what you're looking at, but it's complex. So if we were putting gas into the chamber, we need to maintain pressure. We have to be able to control that. We have to know how much gas we're putting in, how much we're taking out. Hydrogen is going into the chamber, and of course nothing ever bad happened mixing hydrogen with other elements, especially at the temperatures that we have. So we have to monitor not only how much hydrogen we put into the chamber, but if you're pumping it out through your exhaust system, it's not a good idea to blow the factory up because you've got raw hydrogen going out the exhaust pipe, okay? So we diffuse it with nitrogen, and we monitor all those gases in real time to make sure that within safe levels, okay? And we run different tests and pre-tests. And have you ever seen a checklist for a pilot? Okay, for a 747? Okay, and it's a book, he might have about 200 or 300 items on his checklist before he actually fires up the engine. Well, it's very much like that. And so we have to go through them. And then we're always looking for ways that maybe we've missed something in the engineering or in our process, of course, so we're not on the evening news. Well, we'd like to be on the evening news, but not because we've left a black hole in the middle of Mississauga. So we're going to get into design of experiments. Design of experiments. What I'm going to recommend is that what you do is you Google design of experiments, okay, after you've heard me talk. It's not designing an experiment, it's not designing Sapphire, it's how do you conduct the experiment. Sapphire regimes. So this picture here is a typical what you call design of experiments design space, and Paul has attempted to explain this a few times. The feedback we get is that we haven't been that successful because it looks cool, we got some pictures, but if I told you if we increase the voltage from 400 to 600 and set the current from 1.5 or 2 and then set the pressure torr up to 20, we'd get the top middle plasma regime. Okay? And now the eyes start to gloss over. So decided that we'll talk about something that maybe people can relate to. Now, I love sailing, and some of you know that I've done a lot of racing, and I've raced against sailors that have sailed America's Cup and Canada's Cup and the Admiral's Cup. That was our racer back in 2004. A fast boat. It was designed by Steve Killing, who's America's Cup designer. It's a prototype. And so with sailing, you have 4 primary factors. You have wind, water, your sail, and your hull, and then you have interacting factors. These aren't all of them. These are just the ones that you should know about if you're a sailor. If you're designing a sailboat, you can probably multiply that by 10. So these are interacting factors. So we first start off with the true wind direction. Where's the wind coming from? And they say, okay, well then, if the wind's coming from over here, I want to get what's called point of sail, but I want to go over there. I can't go into the wind, but I can get off to the wind. That's called point of sail. So you select your point of sail, and then you have what's called apparent wind, which is actually the wind coming into your sail once you set your point. Then, once you've got that done, then you have to set your mainsail shape and your genoa shape. Those are the two sails, one in the front, one in the back. And the shape, what we're talking about is the actual foil. Okay? So there's a lot of similarities between flying and sailing because those sails are wings. And you want to get a low pressure system on the wing of your sail so it pulls the boat along. So it's another factor. So you have to deal with the shape. And that's what we would call a variable because you can change that. You're not going to change the true wind speed because that's a categorical factor. In other words, it's just there and it's what you've got to deal with, unless it varies. But for the most part, the main sail and genoa shape, there would be what we would call variable factors. Okay? And then once you do that, well then it's called laminar flow over the mainsail and laminar flow over the genoa sail. And it's the laminar flow that gives you lift. And we'll talk about the Wright brothers tomorrow, okay? And what was discovered about laminar flow. And then, well, once you've got that set up and your boat starts to sail, the boat starts to heel. And once it starts to heel, it changes all the way the wind comes into the sails, and now you actually have to set your point of sail again and your sails again because the boat's just changed. That would be like a second order interaction because it's an effect of all these changes have on the boat. Your sails change, now you have to adjust them now because the boat is starting to heel over. And then it changes also the laminar flow over the keel, the rudder, and the hull. And if you get it just right, you can start winning races. It's called being in the groove. And all that equals boat speed. So the ultimate objective is to get boat speed, and you have to consider all these factors and more if you're a sailor and if you're going to win races. If you don't consider these things here and you're a sailor, okay, the stress level is being seen on some people's faces, and this is basically what happens if you don't consider. Somebody who tried to sail and didn't make it. So these are some of the regimes that we get. We get quiescent, we're getting tufting. This is more of an active plasma, you don't see it here. Obviously the famous double layers that we get. This again is more intense. Well, they're asymmetric double layers, but we haven't really looked at the last one very much. So what we're doing is we're trying to classify these regimes to categorize them within, let's say, groups, so that we can say, okay, well, if you came to us and say, Monty, can you give us double layers? We could turn around and say, here's your checklist, yes, and we can dial it all in now. And we can say, here's your double layers. And we can do this as much as you want for as long as you want. So we have very good control over the plasma in there. It's not out of control, okay, which is often typical of plasmas. They're beautiful. We get to watch this stuff all the time. It's such a tough job. What was interesting and mentioned before is that these tufts are actually not sitting on the surface. You might be able to just pick it up here in the top left. You can see it's just actually over top of the surface of the anode, and that's going to become important a little bit later on when we talk about the voltage drop. Boy, does that look familiar. So that's a qualitative statement for you scientists. This here dials to 11, okay? Anybody watch Spinal Tap? Okay, 11? Okay, well anyway, forget it. You can't see it on this picture, but actually there's double layers all within there. But that's the most intense plasma that we have right now. Well, the dials are at 11. So we use design of experiments. We understand the interactions between all the factors in the systems in order for us to be able to get these plasmas. So prior to the formation of double layers, the plasma is not stable, which is something that was interesting, and we're going to be getting into that. Michael's going to show you the analysis on this later. The formation of double layers causes the plasma to stabilize. So once the double layers form, we see a voltage drop, and Safra is saying, I'm good. You know, it doesn't want any more voltage. It just says, I'm satisfied with what I've got. You can turn it to whatever you want. It doesn't matter. It doesn't want it, which is quite profound. So the response is being the trapping of ions and electrons within the double layers, and once that happens, it stabilizes. So that's like I said, second order reaction or response. A complete change of the voltage and current relationship. Michael will talk about that. Radiation hydrodynamics. Like I said before, you get all the fun stuff. Right, okay.
So this is a good example of how the physics we inherited, so to speak, it maybe is not always so predictive. And so we use our chamber as a laboratory to observe phenomena, and then sometimes we can go back and fill in some gaps, like how did this happen from a physicist's point of view. As Monty will say soon, we destroyed quite a bit of equipment in our chamber, and it wasn't so clear to us how it could be happening, because there didn't seem to be enough energy present to do some of the damage that we were seeing. So Lowell Morgan went back and did a radiation hydrodynamic analysis of it. And what came out of that, which was a surprise to all of us and quite wonderful, is that the chamber, the discharge in the chamber, is slowing down the passage of ultraviolet light. So optical light just goes straight through, no problem. But there's a particular frequency, the 10 electron volt, which is very high energy, ultraviolet light, that gets passed on very slowly from atom to atom. Even though it's not a very dense plasma, the cross-section is so high that a photon is emitted and immediately absorbed by another hydrogen atom, which means if you are an ultraviolet photon, it takes you 60,000 times longer to get out of our chamber than if you're an optical photon. Okay. That sort of slowdown in the velocity of light is something that is often attributed to what we think we know about the sun, but to see it in our chamber here is a pretty exciting result, and the amount of energy that is stored, well, you remember the discharges. You have to think about those layers, the discharge, that's what your eye is seeing. What your eye can't see, our eyes can't see, is, so to speak, this hidden or trapped or stored energy, very high frequency energy, that's just waiting there in the plasma for something like an unsuspecting piece of equipment to encounter it and then destroy it. So Monty will tell you about that. This is you, right?
Yep. Predictions in thermodynamics. Some of you may be familiar with what's called computational fluid dynamics. We use it in thermodynamics, we use it in gas flow, we treat liquids and we treat gases similarly. It's used for optimizing the speed of sailboats. It's used for laminar flow calculations over fins on high-speed fighter aircraft. It's used for those kinds of things which are fluid, you might say, or what we call boundary conditions. There's a lot that's been learned over the years in thermodynamics and being able to create modelers that can actually very accurately predict what is going to happen under certain conditions. The calculations we did showed that the responses that we got on the chamber, because we have temperature responses, I don't know if you saw that or not. So 110 degrees C, but we have thermocouples all the way around the chamber to measure the temperature of the chamber. These numbers are pretty accurate, okay? In other words, we created a model, we run Sapphire, we run it for a period of time, we should start seeing temperatures like this, and we do. So we're happy. Well, this is called gas flow. We are able to accurately predict that the gas flow inside Sapphire is very, very slow. It's not suffering from any kind of thermal buoyancy, which means when you're looking at Sapphire, it doesn't look like it's suffering from gravitational forces. It's a big deal. Temperature. So that's a good one. We have a probe in there. We want to make sure the temperatures are good. 2,300 degrees Celsius is what the CFD is predicting based on all the information we put in there. But what really happened? And this is what really happened. So we put the probe in, and we're measuring the plasma, and things seem to be fine. Just look for a little... and then it's no longer there. So it was not a magic show. It's just one minute you see it, now you don't. So this here was approximately 182 watts. You saw the size of the chamber. That's 182 watts of energy displaced through that whole chamber. And that's what it looked like afterwards. And we said, there's something wrong. Okay, it shouldn't be doing this. Tungsten shouldn't even be reaching thermal temperatures to vaporize tungsten like that. But we did, with 182 watts. Some people have 200 watt light bulbs. Well, this is a 182 watt light bulb, and that's what happened. And by the way, the probe isn't grounded. It's floating, okay? Meaning, if you know anything about electricity, if you've ever plugged something, or like say a paper clip into a light socket, you'll find it very quickly what happens when you have something that gets grounded, okay? Something's going to light up, okay? But this isn't that. This is floating. This is what we call floating potential. But it happened before, after. We went through a number of these. We called our supplier, and he says, well, your plasma's too hot. But it was designed for that, you see. It was designed for this plasma. So we had to create new and improved, more robust Langmuir probes. So that's it. And at the tip over here, underneath it, we have two sets of fiber optics, but one is actually pointing to intersect with the tip. Okay, so we're looking right down at the tip of the Langmuir probes. When we put the tip into the plasma, we're also looking at what's going on in that tip, not just electrically, but optically as well. And further back, right beside it, is the mass spectrometer, so we're actually sucking gas out of that area too as well. So we're pretty happy with that. We thought, okay, we're ready to go again. We were able to capture this. It's a plasma, as you can see. If it's white, it means it's hot. And we said, okay, well, let's put the probe in. And let's just see. We're getting measurements, and we're happy because the numbers are crawling back, you know. And we're saying, okay, what? So, and then we didn't change anything in the chamber. It's just, this is a response. And we're like, so we just smoked 2 weeks worth of work, about $10,000 or so. But what was interesting is that the probe survived. It looked like it survived. But you notice the crater on the side of the anode, and we're going to come back to that in a minute. And this time, so I'm going to go into this. I'm going to show you here something. It's about thermionic emissions, which you get from a light bulb. Now, remember, the probe is sitting in a floating potential. It's not part of the electric circuit, but the anode is. So I look at this and say, why? That big ball there is thermionic emissions. The probe is inside there, okay? Why is it so bright compared to the anode? We're starting to ask questions like it really shouldn't be doing this. We get some really cool artwork. I'm thinking what we should do is get this printed and frame it. It's just beautiful. Like I said, it cost $10,000, so maybe we should. Yeah, T-shirts. Yeah, tungsten tips. So we finished with the test, and we decided, okay, so this is what tungsten looks like. It's kind of a sintered look, okay, before and after, and the blue. And I thought, okay, I've seen this kind of thing before, where you anodize materials and they can change color. And it didn't look like it suffered because those vertical marks are really from a diamond wheel. So I recognized those, and it doesn't appear to be any degradation. And the alumina looks like it got melted, so I know, okay, well, it's pretty hot. But then I tried to pull the probe tip out with my pliers, and it just crumbled in my hand. It was really weird because you can have arc welders and arc welding at 19,000 degrees, okay, and TIG welding. That's some of the hottest temperatures, but those tips will last 20, 30 minutes before they have to take them over and grind them, but they don't just crumble. So there's the difference between the two, and I looked at it, I thought, boy, that's really strange crystalline structure, and decided, well, I don't even know what this white stuff is, never seen this before, and decided to take it down to the University of Toronto and do some scanning electron microscopy. And this is what I found on the inside of the probe tip. This is tungsten. We're calling this shale. We're not sure what that is. And then we took a look at the anode. This is where the crater was. And I've said before, Makes for great artwork. But these are the true colors, by the way. So we thought that this here was copper, but it's not copper, actually. It's iron oxide. So I decided, well, I'm just going to pick a spot. Picked a spot, and I said, gee, that's interesting, the top of that little mountain there. Went in to take a look at it. I saw these little nodules, which I thought were strange, and then put that under the SEM. And if anyone knows anything about scanning electron microscopy, normally when you see a bright spot like that, it means that it's usually a fairly heavy element, okay? And so this here is a scanning electron microscopy here. This is normal iron. This is the anode. This is the top of Mount Michael, okay? And then these are some of the things we're seeing. Some of this is the chemistry. Now, why I showed you the iron is because iron doesn't have this chemistry. And it sure doesn't have this chemistry. And what blew us away is that we knew there's certain error margins with SEM. We don't know where the barium, the titanium, and the calcium came from. We have some ideas about maybe the carbon, but these elements were not there, and what we don't know is why they're there in the anode. I'm just going to skip over this quickly. Similar, but what you see here right now is we're doing, looking at the chemistry if there's any changes. So we built a new probe after all that. It did survive, and we're working on understanding the voltage drop. Don Scott was predicting there should be an extremely high voltage drop just off the surface of the anode. We didn't know. We have no judgment. We just take a theorist's position at face value. So we go in and we explore these things. The first probe, as you can see here, the tip is long. We've got kind of an average voltage drop off the surface of about 30 volts, and then we discussed amongst ourselves how we're going to deal with this. What if we made the tip really, really short? And so we did. And so that's the short tip. And so we got closer to the plasma, and we measured 270 volt drop, and it came right back up. Now these aren't absolute numbers. What you're looking at is the delta, or the change, the difference between those, what we were able to measure. It could be higher, but that's what we were able to look for right there. And then we pull the probe tip out with our gimbal, and Michael will show you Michael's analysis says about all of this. There you go.
Couple of charts looking at overall chamber parameters. One of the reasons we're doing this is because, as Waller Dono said, that electrical engineers should be astronomers and vice versa. So part of our mission is to forge that bridge, to give that crossover, and ways for each camp to think about the other's data. What we're looking at here, the measurements in the chamber, you can see in the bottom there are 4 different regions of discharge that I'm mapping out here. The red line is the current. Okay, in this experiment, current is our driver. That's the lever that we are turning to change the situation. And the current's going to go from about 2 amps up to about 6 amps. In response to that, the blue line is the voltage across the chamber, across the entire discharge. And that voltage rises, as you can see, from about 300 to 450 volts, and the discharge, the nature of the discharge changes. You can't see it here, it's still, but that second picture, it's moving. It's a lot of movement in that second picture. Very complicated pattern changes. Crank up the current some more, up to about 12 amps. New response from the chamber. Looking at just the voltage piece of it, you can see the voltage kind of goes through a couple of different changes there. All of that is the plasma creating those double layers. It's changing the nature of the discharge to accommodate the extra current, the extra energy it has to process. The wiggle, we don't know about the wiggle. That's to be discussed later. It's not the power supply, it's the plasma, but we don't know why it's doing that right now. And this last bit, that's pushing over the edge past this stable region into a discharge, arc discharge. So at the end of that, everything falls off in a bright bolt of lightning. If we look at the resistance of the discharge and the power being consumed by the discharge, this is a different lens we can bring to the situation. The green line is the resistance in the chamber discharge. The black line is the power. Same regime, same experiment, but now just looking at these two other variables. And you can see that the resistance going from the first phase to the second phase, the resistance goes way down. So this change the plasma does is a way to bring down the resistance in the chamber. The power, you can see, goes way up. It's a way the plasma is adjusting itself in order to process more power, to allow you to put more energy through it. The resistance goes down even more, heading towards the double layers, and the power consumption going way up. So what does all that mean? That's what we're thinking through. But in basic terms, the plasma adjusts itself through an enormous range of stability. We can go from 1,000 watts to 20,000 watts, and the discharge is happy, it's fine, and it's changing itself constantly to be able to accommodate that power, whatever power you give it. It's a very stable system. This is looking at that Langmuir probe when we pulled it out from the anode. The red line is that potential Monty mentioned, the change in potential. It goes from about 300 down to 0 as you move away from the anode. From that, we can calculate what's the strength of the electric field in there. Changes in that potential, they correspond to or are linked to changes in the electrical field in the chamber, which is the green line. And in this particular run, about 8,000 volts per meter for an electric field, which for any astronomer who says that space can't support strong electric fields, this is an example we can say, well, a plasma of our design can support very strong electric fields without discharging, without arcing. It's happy to keep them there in a stable state. The black line is the charge density. This data didn't get us in close to the anode, but it drops way down, goes off the graph, the charge density. It's just not on this plot here. The blue line is the resistance, which we measured with our probe. I don't think anybody's ever measured the resistance of a plasma in discharge like this. This is the data we got. What does it mean that it follows that particular path, which seems kind of related to the other parameters? We don't know yet. This is new data, breaking new ground here. Electron temperatures. You can see that the electron temperature goes up as we move away from the anode. So this was back in the beginning. This was one of the classic questions, right? The temperature inversion, the temperature anomaly. Why would the sun get hotter, the atmosphere, as you move away from it? Is there any way to explain this? So we didn't set out to prove that. We simply took this electric sun model, lit it up, and then we measured the temperature. And our electron temperature of the electrons in the chamber, goes up considerably as you move away from the anode. Now, why does that happen from an electrician's point of view? We're not so sure yet, but the fact that we see it right out of the box, so to speak, is very exciting. That temperature, this is farther away, closer to the anode is over here where it goes up higher, but that temperature close to the anode corresponds to 81,000 degrees. If I were an astronomer and I saw this system, I would say, oh, the temperature of your corona just went up to 81,000 degrees. And then we have that in a stable state in our chamber. What 81,000 degrees means, we talk about temperature a lot.
Yeah.
And we all realize that temperature was developed to describe steam engines, and it does a great job describing steam engines. Perfect, right? Can we take that idea and bring it to the solar world? This is one of our after-hours discussions that goes on for quite a bit. Okay, you may have heard that there are some problems with the nuclear fusion model for the sun. Like it predicts almost nothing about how the sun behaves. The fusion model may not be able to predict sunspots or coronal loops or the relative abundances of the elements in the photosphere. It may not be able to predict the 11-year cycle of the magnetic field or the amount of convection underneath the photosphere or the existence of a photosphere. It may not be able to predict the existence of a chromosphere or corona or the temperature profile of the sun's atmosphere. But If you assume that hydrogen is fusing into helium inside the sun, then you can predict how much energy the sun will give off. And that is good. That is really good. So good, in fact, that no other physics model for why the sun shines has been so good at predicting this one basic aspect of the sun's behavior. So the fusion model for the sun will have egg on its face all day long, but until some other physics model can quantitatively describe the basic energy output of the sun, then no one is going to be changing any physics textbooks.
As you know, the SAPPHIRE team is investigating the electric sun model. Here is just one of the many questions we are investigating.
Again, small chamber, big sun. The surface area in the SAPPHIRE chamber is about 10,000 square centimeters. Can we use this to predict what the size of the sun should be if it were an electrical discharge? See, that would be fun because no one in 100 years has done such a thing successfully. But we're going from 10,000 square centimeters to 6 times 10 to the 28th square centimeters. That is a very big leap, okay? To add 24 zeros onto anything you're doing in the laboratory, that's pretty bold. Okay?
I think so.
Okay. Yep.
3 minutes. Okay. We have 3 minutes.
You can do it.
Yeah, I can do it. Presentation summary. Wow, we're there. Okay. Quickly. Okay, SAPPHIRE, contain, control, stabilize energy, dense plasmas. Chemistry changes. I forgot to go back that slide.
Tomorrow.
We'll do that tomorrow. But anyway, we're seeing some really interesting chemistry in there, and there is significant atomic mass of 3. We don't know what it's about, but it's there. That's a big deal. Chemistry changes, slowing the speed of light, variations in electron density comparable to the photosphere, heliosphere, and nuclear bombs. Double irradiance. That was great work, Michael.
Thank you.
When we heard this back, Paul and I checked, he said, Monty, you got to see what Michael did. So it's a big deal. Confinement of high-energy photons, photon trapping. Of course, SAPPHIRE is cooler than its surrounding atmosphere. Isn't that interesting? Because the further we look into the sun, the colder it gets. Same behavior in SAPPHIRE. And we turn the volume up here about 1,000 times. It's what it's like being in the lab sometimes. But it's stable. Now, what I'd like to do is freeze this just for a second. Now, Lowell had predicted, and I know there's some electrical guys that really have an issue with this, but what you're looking at here is that this cathode here on the left has gone dark. Most of the electrons that were feeding the plasma all the way up through are coming from the copper cathodes. These cathodes are, they're pretty big around. But what we're discovering is that what Lowell had predicted is that at some point in time we may not need cathodes in SAPPHIRE. That the electrons that are being trapped in double layers is actually what's feeding SAPPHIRE, that's feeding the anode. But what we're seeing here is that we start making some parameter changes. We're going to explore that this year. We'll see whether or not, we're getting, there's theoretical sides to this, but what we're seeing is the majority of electrons that are feeding this plasma here are coming from the plasma itself in these double layers. It's pulling material into the core. So just something we're looking at. And that's it.
Our next speaker, giving his second lecture at this conference, is Montgomery Childs, going to tell us about collaboration and science. He's got a lot of experience on this score, particularly as being the CEO of Altus. So put your hands together, please, for Montgomery Childs.
Good morning. Let's see how we do this again. Cigar. Now, some of you see that I smoke cigars. I'm going to get back to the cigar, and we're going to talk about being sensitive to what nature is really doing. You also know that I sail. And that's our sailing mode. This is a racer. It was designed by Steve Killing, who designed America's Cup. It's not wooden. It's actually just a veneer, but it's a special design. We won the Cup in Canada. A lot of flags. It's got a lot of mast. But to learn how to sail and race at that level, it takes a lot of skill and it takes a lot of teamwork. You need 4 or 5 people. It has to be very coordinated. So we got a coach, and his name is Mike Wolfs, and he's a Canadian silver medalist, Olympic silver medalist. And so if you want to learn how to do something, you want to get the best people to teach you, if you can. Somebody that's got a track record. So he's teaching us for 2 years. And there was one time we were out on a Saturday afternoon, the whole team practicing, and there's no wind, no apparent wind. And he says, Monty, it's easy to sail when you've got a nice breeze, but when it's like this is where the championships are won. And so I'm going to show you something. He says, anybody here smoke? Well, 4 of us put our hands up, okay? We lit up a cigar, we held the cigar up. He said, I want you to show you this, because the sails were just hanging straight down. So we waited for a second, and we watched the smoke just drift off to the port side. He says, okay, everybody off to the port side. Now, anybody that's into sailing, normally you're going to go on the windward side to counter the forces. But what happened was we get on the leeward side, boat heels over just slightly, the sails just slightly start to bag. And then they start to fill with the wind. And then we start to move forward. 0.1 knot, 0.25 knots, half a knot. And so interestingly, in 2004 when we won the championship, the day of the race, the first race, there was just a very light breeze, enough to get through the start, and then it just died. So we lit up a cigar. Everybody got over to one side of the boat. There's 30 boats in these races, and these races are 40 miles long. So we race across Georgian Bay. If you have an idea how big Georgian Bay is, it's about 300 miles long, and it's about 80, 100 miles across, okay? So these are big races, not around the mark, okay? And so for the first hour, that's how we sailed. And we left the rest of the fleet behind over 2 miles. We're not talking seconds or anything like that. And so that's actually how we raced. And we took the Cup that year because we learned to tune in to evidence and see what it's telling us, which is really what we're doing with Sapphire, okay? So what I want to discuss is the difference between consensus or fact. So it's generally accepted fact that the universe came into existence out of nothing. Now this is contemporary, so we have nothing. A guy like myself would ask, well, how does it come out of nothing? But it's also a generally accepted fact as a consequence of the Big Bang, gravity is the genesis of all that we see. And this is all that we see. There's a lot there, and that's supposed to be due to gravity, and that's supposed to be due to the Big Bang, and all this came out of nothing, randomly, of course. And so it's a generally accepted fact that the core of stars became nuclear as a function of gravity. It's a generally accepted fact that black holes, dark matter, dark energy, and other dark things are responsible for making the universe work as it does. So we have black hole, which is really nothing. They've never been measured. We have dark energy, which is another variable in a mathematical equation. And we have dark matter, which is also another variable in an equation to try to make sense of this universe that we see that came out of nothing. And of course, other dark things. So, but it was also a generally accepted fact that you could not sail faster than the wind for thousands of years, until recently. It was also a generally accepted fact that heavier than air aircraft could not fly until the last maybe 100 10 years or so. So we have two worlds. We have the theoretical and we have the empirical. I'm an empirical experimentalist. But like Newton, we don't deny the theoretical. We accept it as being necessary to develop ideas about what is going on in the world around us. I feign no hypothesis, and I contrive no hypotheses. I have not as yet been able to discover the reason for these properties of gravity from phenomena, which is his test. And I do not feign hypotheses. For whatever is not deduced from phenomena must be called a hypothesis or hypotheses, whether metaphysical or physical or based on occult qualities or mechanical, have no place in experimental philosophy, which is, in today's day and age, you might say is the scientific method. So these two worlds have been at war from the beginning of time. You have the theoretical, which is in modern terms called philosophical methodology, and empirical, experimental philosophy, the way you go about doing experiments. So philosophical methodology relies mainly on a priori justification. It's relating to or denoting reasoning or knowledge that proceeds from theoretical deduction rather than from observation or experience. And sometimes it's called armchair philosophies. While experimental philosophy makes use of empirical and experimental data. So you may say gravity exists, and you may say that the evidence indicates that gravity exists universally. But you may not claim that gravity is the primary driver of the universe. To make this claim means that gravity is the genesis of electricity and light, and that electricity and light are responses to gravitational forces. But there is no scientific data that gravity alone is a genesis of electricity and light. Do you have any water here at all? Oh, thank you, Michael. Is this bath water?
It's genuine bathwater, honey.
Thanks. So I want to get on to Albert Einstein because a lot of people criticize him. But what he had said is that all knowledge of reality starts from experience and ends in it. Propositions arrive at by purely logical means are completely empty as regards to reality. This is Einstein. Because Galileo saw this, and particularly because he drummed it into the scientific world, he is the father of modern physics, indeed, of modern science altogether. But he went on another lecture in Oxford. If you want to find out anything from theoretical physicists about methods they use, I advise you to stick closely to one principle. Don't listen to the words. Fix your attention on their deeds. To him who is a discoverer in this field, the products of his imagination appear so necessary and natural that he regards them and would like to have them regarded by others not as creations of thought, but as given realities. This is Einstein, and he gets a lot of criticism, but he did hold to another view, and he questioned his own theories.
You need to know that black holes, dark matter, dark energy have never been measured. They're mathematical variables in mathematical equations that have been deduced. This may be acceptable as philosophical methodology, but it is not the scientific method and cannot be promoted as scientific fact. These claims have nothing to do with empirical science and are completely empty as regards to reality. It doesn't mean they don't exist, it just means these things do not qualify to be promoted as scientific fact until they can be measured and quantified as contributing factors to the natural process.
And we do theoretical physics, computational fluid dynamics, and it's a tool, but it doesn't quantify what is going on in sapphire. The humble hydrogen atom. We have a proton, we have an electron. The electron has a negative charge. We don't know why. We suspect a proton has a positive charge, and we don't know what that's about. We don't know why it is that positive and negative are attracted, but we know they are. And if we stretch the electron out from its orbit and it wants to come back in, it releases a photon. And some would say that a photon is a particle. And so I asked a physicist one day, so I said to him, well, if we excite a hydrogen atom and we can do it indefinitely. And he says, yeah, we can do it indefinitely. I said, so, and it's a particle. I said, yeah, and it creates a photon. I said, creates a photon. I said, that's really interesting. So does that mean that the hydrogen atom has an unlimited supply of photons? Now this guy has got 83 papers published, peer-reviewed. He was the editor of the IEEE, really good guy. But in that question, there was that 3-second silence that felt like an eternity, because he knew where it was going. So I said, does this mean that it has a limited supply of photons? I said, or does it create them? And even that was a silence, because what we're saying in effect is that when we excite the hydrogen atom, we're creating a particle out of nothing. Being an experimentalist, I'm cool. Like, I don't have to have the answer. And so we just left it at that. So questions in my mind came, well, if it's creating a particle out of nothing, does that mean that when we create light that we're actually adding mass to the universe? So it's okay if you don't know. It's not okay if you think you know and really you don't. Knowing something is a result of conducting a scientific method, investigating natural processes, so we collect data. And you do it all the time. You make decisions based on information that you have coming into you today. So it's a generally accepted fact that heavier than air aircraft could not fly. And we have the Wright brothers, and we know all about them, or do we? The Wright brothers, a couple of bicycle mechanics, they're not physicists. They're not mechanical engineers. We're inspired by what they believed could be. But instead of promoting theoretical postulations, they got to work testing, a lot of testing. And long before they were ready for Kitty Hawk, and long before they built Flyer 2 and the Silver Dart, they had a lot of problems. Lilienthal, I think is the name. Lilienthal, very good. So they had, at the time, what they believed from a theoretical perspective, quantified what it took to do flight, controlled flight, but flight. The Wright brothers used these equations and discovered early on, after they crashed and got bruises, that didn't work so well. So they got busy. They're out in the fields of Dayton, Ohio, watching eagles and other birds fly. And they're studying how they fly. And one of the testimonies is when they're watching the eagle fly, they're watching what I call the fingertips of the feathers, but watching them just move the end feathers a little bit as they glide through the ether, or the air, what they would call ether. So they looked at the form of the wing, and they looked at controlled flight, and they got busy and they said, okay, enough of the crashes, let's build one of the first wind tunnels. And this is actually a picture, it's out of NASA. If you go to NASA website, they've got a real beautiful section on the history of flight. So they tested many different shapes and forms, and the speed of the wind, and lift, and the camber, and they devised their own formula and quantified what they believed would be the formula to give them lift and flight. And this formula, and there's variations of it, are the base formulas for all aircraft today. Now, they've been refined, of course, and I'll get into computational fluid dynamics and sailing and other things, but the more you discover through scientific method, the more advancement you can bring, more technological advancement to humanity. But you can't allow theory to box you in. So here's the first flight. It's amazing. And then when they were done, they took it to France. America didn't really support them. They said, okay, we can't get funding to do this, so they took off to Europe, and there's a whole story about them traveling around while their sister was giving them heck because they were starting to enjoy themselves too much. They enjoyed some of the French wine and things like this. But so to prove their point, they started flying around the Statue of Liberty. So we did it. And the age of flight began. Faster than the wind. Up until the last number of years, no one believed it was possible to sail faster than the wind. It was originally hang up a sheet. My goodness, the wind blows us and the boat's moving. And then people kind of devised different ways of trying to hold these sails up. And this is an artist's, I guess, rendition of the Santa Maria, which had a speed of about 4 knots, okay? If you do the calculation, it took quite a while to get across from Europe to the Caribbean. But with studying science and studying the properties of nature and starting to quantify them through testing, you can develop some pretty cool math. So I'm going to play this. I think if I could play this right.
A little bit of both. So as you squeeze it in, off goes the boat. The second thing is the foils. Once we can lift these hulls out of the water, they're on these tiny little foils, and that cuts away a huge amount of drag.
The foils are so small, and they wouldn't work unless the water was 800 times as dense as the air, which is the situation we had. So you really need not much more than 1/800th the area of the foils to what you have with a wing.
Once the boat starts to get going, it starts doing 10 knots, then the boat's effectively seeing 20 knots. So that sort of circle just keeps growing. You start accelerating, the boat goes faster, it sees more wind, goes faster again, so you get more power, more lift.
And this is a continual action. It's not just one squeeze. It's happening every second of the yacht race. The wind is coming from one side, the water's coming from another, and the yacht's continually being pushed forward.
It really just powers itself up, and the faster it goes, it just seems to lose more and more drag.
If this was exactly 45 degrees, then the speed of my squeezing would be the same as the speed of the yacht. The key to going fast is to bring this angle closer together so that for a little movement this way, which is the wind speed, you get a greater acceleration and a greater speed that way. So you make these angles finer.
So I know it's a strange concept that you can go faster than the wind, but in these boats it's very easy to happen.
And the question is, how fast? And the answer is as fast as you like, within limits.
Very cool. Too bad Christopher or some of the other sailors back in the old days didn't know what we know today. But from a scientific perspective, from an experimentalist and someone who does engineering and computational fluid dynamics and FEA and all these things, this is what you would call a design of experiments nightmare, okay? And the reason why it's a nightmare is because yesterday I gave you a few of the factors involved. So the Wright brothers identified certain factors. They discovered that there was certain mathematical ways that they could quantify the camber and the shape and the area of the wing. The same thing happens in sailing, but sailing is actually even more complex because you have so many interacting factors at the same time. And what you want to do is you want to optimize the speed of the boat. You want to get it as fast as you can go. So what are those factors? How do you quantify them, and how do you change the design? So you come up with a design, and well, as I was saying, these are just a few. There's a lot more. And you have to put them together in a kind of a recipe, you might say, and develop a design, a soft prototype, which is a computer model, which is what a lot of, you might say, theoretical physicists do today in the contemporary model. But you have to test it. You have to see whether or not it has legs, as we say. So computational fluid dynamics, and this is just one tool of many, and these are very powerful tools. So you look at the sailboat, you can put it in the computer model, and you can actually look at the laminar flow, which is the green part as it goes past the top of the wing, because this is a vertical wing. So you see some of the math came from the Wright brothers. So you have laminar flow, which gives you a low pressure system on the sail that pulls you forward. Then you have a second sail, and you look at the actual interaction between the sails. And then the next slide, well, when the boat starts to heel over, that actually changes all of those factors again. And then you have to trim the boat. So the models become quite sophisticated in that we can predict in one position or another position what its effect is going to be. Ultimately, those foils, they're like horizontal aircraft wings, but they're designed to go through water, so they're very thin. I don't know what they make them out of, likely carbon fiber. But the idea here is that the laminar flow over the water gives the keel lift. And we experienced that with the Dawn Treader, like the boat that we had. It was a specially designed keel. We heel it over, and in light winds, the boat would actually start to come out of the water. So we decreased the drag. And that's a picture of the foil there. And it comes out of the water very fast and very high. So this one here is a world record.
Okay, she's smoking. All right, this is fast. This is fast. This is nice. This is real fast. Goodbye, helicopter. This is real fast. This is how you do this, Chucky. Up down. Up down. That was quick. That was quick. That was smoking. That was rapid. Well, all right. Alright, that's what I'm talking about, Marco. Unbelievable. Unbelievable. That was worth every minute in that build shed. That was an awesome, awesome run. That was just...
Experimentalist.
What was it, by the way?
Well, he had a 23 knot wind, which translates to about 42 kilometers, I guess. And he top speed, I think it was 127 kilometers an hour.
Whoa.
That's the wind. So I figured it would take in Columbus just a little over a day. And he would have been saying, "It's fast. It's very fast." So whether he discovered, the New World or not for him, I'm sure he would have done it again just for the thrill. So this is where I'm gonna put a kind of stake in the ground, and I'm gonna say things that the experimentalists, they're the gatekeepers. They do hold the keys to progress in applied sciences and technological advancement. Experimentalists can't say yes to black holes, and we can't say no to black holes, any more than we can say yes or no to the EU without testing their models. So as Newton, the Wright brothers, Einstein understood, the two worlds need to be brought together. There must be a collaboration for technological advancement to be realized. You can't have one without the other. And I'm a true believer that science is to serve humanity. Humanity is not to serve science. Science is a very amazing tool. It's to serve us. So Sapphire, back in 2011, I did an evaluation. So when you're going to test something, somebody makes a claim, you go faster than the wind. You're thinking, well, okay. Or in Sapphire, the universe is electric, the sun is electric. There's a few tools, modern tools, called design of experiments, that you can actually filter through the hypothesis to see whether or not it may be a testable model or not. Because it's not testable, it doesn't mean it's not true, it's just we don't have the technology or the wherewithal or the way to conceive the hypothesis could be tested. So I did an evaluation, statistical, filter tests, and analysis of variance based on Hertzsprung diagram and a bunch of other things, and came to the conclusion that if I broke the electric universe model down, I had two primary factors of charged plasma affecting matter of a different electrical potential. So if you have this delta between the two, kind of like the wind and the water, those are the two basic factors involved, and you start from there. So then I started to develop a model and looking at prior science like Birkeland, Quinn, Fiorito, so many others that have been doing plasma. Most of it was cathode-centric, you might say. The electric universe model is anode-centric. So there's a bit of risk in there to say, okay, how's this going to respond? We didn't know how it would respond, but obviously it's doing extremely well. But Sapphire is more like sailing in that we're looking into the way nature does things. We're not trying to force it. And Michael said last year, it's like breathing, it's natural. It's like we're not trying to push it and smash rocks together. And we're not using a large motor, to power us through the water. We're trying to work with what we see the plasma wants to do. We're trying to feed the plasma what we think or have some ideas as what it would like to do to become organized. And then we're monitoring those parameters. And that's how a design of experiments is done. And we get all that data back and we can control it. I would say maybe a better would be to honor it. Okay? So we're not trying to get the plasma to organize. It likes to become organized under certain conditions, whatever that means. So Rupert and some of the others might have some thoughts on that. So we're not doing this. We're not trying to do something special. It likes to form these tufts. We don't understand them. But we're looking at them. They become organized. Their fields are uniform and that they like to be separated. As Michael said, some of the energy and the densities that we have, we say now are comparable to what we see with the sun. It's pretty amazing, actually. We're not trying to get unusual chemistry. Now, this is controversial. I can't really talk about too much at this time yet, how we got this. But what I can say If some of you are familiar with mass spectroscopy or residual gas analyzers, you'll know what you're looking at here. We started off with a chamber in pure hydrogen, and we baked it out for a couple of days. Then what happened is we said, okay, well, the chamber's clean, it's purged, we put hydrogen in. Mass spec is saying you have pure hydrogen in the chamber, 100%. We thought, okay, this is a great starting point. So in that, we said, okay, we knew that there's something that we could do. We introduced another gas, and we got our double layers to form. And then we just let it sit there and bake for a few hours. And it didn't change. It was just extremely stable. Then we thought, okay, well, we know that there's another thing that we can introduce, another gas that we can introduce that will disrupt the double layers. Okay, they'll start to break down. So we did. But before that, the mass spec is sitting out here and it's reading only 100% hydrogen, even though we introduced this other chemistry. We didn't read any of that chemistry in the chamber. It only read hydrogen. We introduced the second, and the moment the double layers disappeared, we got this. And as you can see here, we have atomic mass of 3, 14, 15, 16, 17, 18, 20, 40, 30. We have some other stuff as it's moving along, and it stayed there, and it was stationary. Like it stayed there. What was interesting is that the hydrogen, the two other gases that we introduced, stayed at the constituent percentages that we put in there. So we registered those later on. It doesn't show on this screen here, but the percentages stayed the same. But the one element that dropped from 100% down to 39% was hydrogen, and all these new elements formed. Now, we're not making claims. We're just saying, this is what happened. And then, of course, there's the barium and the whole titanium thing, which we know we didn't have in the chamber. So why it is there now on the anode or not,